went to the University of New South Wales, where he spent 3 years, from 2014 to 2017. And since then, since 2017, he has been in Academia Sinica, ACA, in Taipei, Taiwan. His research interests are infrared and submillimeter observations of debris disks and interstellar dust. And today he will tell us about a class of objects called Little Dippers and one object in particular. So, please.
Thank you very much. And thanks for that great introduction, Sinica. So yeah, I'm going to talk to you a little bit. It's a kind of new thing I'm working on at the moment. I'm normally dealing with cold debris disks or remnants of planetesimal belts that are kind of analogous to the asteroid belt and Edgeworth Kuiper belt in our solar system. And so this is kind of a new thing I'm talking about today, which are these little dippers, as Sinica said, which are much closer in and much more extreme and much more dynamic than the usual belts I'm used to dealing with. So it's kind of exciting new field in kind of debris disk studies. So first off, yes, there we go. So first off, let's give you some context. So we start off, obviously, your molecular cloud collapses, produces a star, and around that star, you get a protoplanetary disk, which is the interesting bit. And in that protoplanetary disk, you get dust grain growth, transformation, and alteration of material from tiny, fluffy, submicron dust grains collected from the interstellar medium, and then processed up into bodies, planetesimals, cometary bodies, and things eventually the size of planets, and to Jupiter sizes or beyond. And so it's in that process that the architecture of your planetary system that you eventually get on the main sequence is formed. And that is broadly dictated by the metallicity of the cloud that collapsed, so the amount of solid material you have to produce planets in your protoplanetary disk. And it's also dictated by the structure of that disk, so the temperature structure dictated by the central object. So the more luminous star in the center, you get a different temperature gradient than a less luminous star. And so the interesting thing for me is taking these protoplanetary disks where we have very, very young the initial snapshot of the planetary system that will then eventually become something similar to our own solar system. And there's a big question, of course, of what happens in between. And one of the best ways we've got of looking at that is by looking at obviously other planetary systems, because they're basically a kind of a similar version to the same processes that happened around our own solar system. They just show different outcomes. So by looking at enough planetary systems, you get an idea of all the possible outcomes of what planet formation and planetesimal formation in particular could produce. And so one of the best ways of doing this is by looking at the dust emission, because it's much easier to find debris disks, broadly speaking, than it is to find planets, because your debris disks are big and bright, and as long as you can get to infrared wavelengths, which usually means going into space, you can sort of see the warm emission or the re-emission of stellar radiation by these dust grains as an infrared excess over the stellar photosphere at these longer infrared millimeter wavelengths. And by tracing both the emission profile of the dust that you see and its spatial location, so with multi-wavelength spatial resolution imaging, you can then say two things. One, you can say what the structure of that disk is, and B, you can say, well, if is dust there, there's probably not planets there. So by finding out where the dust is, you find out where the planets aren't, or where the planets might be, depending on the structure of the disk you're looking at. And it's kind of an iterative process here, just on the right. You sort of pull back into looking at disks, looking at planets, and they're interlinked. As you know from the solar system, where you've got the structure of the Kuiper belt is dictated by migration of Neptune into it, and you've got the asteroid belt with its Kirkwood gaps dictated by the presence of Jupiter. So in your protoplanetary disk, as I said, you've got dust grain growth from the stellar medium up to larger solid bodies. These all happens in the mid-plane where it's cold and relatively not stirred, so you get a higher dust to gas density reaching unity, and then supposedly the best mechanism right now for planetesimal formation is streaming instability, where you get centimeter-sized bodies or millimeter centimeter-sized bodies that then collect and collapse into kilometer or plus-sized planetesimals instantly, without the need for growing through meter-sized boulders, which would be very quickly migrated through the disk radially and then destroyed due to gas drag by hitting the central star. And so in this protoplanetary disk, the important thing to notice here is that different wavelengths probe different structures, and that most of the action happens, as far as the dust is concerned, in the midplane. So your temperature structure dictated by the star, not shown here, it tells you, basically where stuff is going to happen, because most of the action in terms of dust grain growth preferentially occurs at pressure bumps. So where you've got ice lines where solid density of material increases because you go from a gas phase to a solid phase for ices, volatiles like water, carbon monoxide, that kind of thing. And then at that point, you get an increase in the density of step function, increase in density in solid surface material. That encourages grain growth, and then that encourages more material to grow at those locations. And you can trace those at millimeter wavelengths. So if you look at a nicely selected sample of protoplanetary disks here, this is from the D-Sharp survey by John Andrews, you can see lots of ring-like structures. That's good because we expect ring-like structures from the temperatures. However, if you look on the right-hand side here, you see that this ring-like structures on the left do not correlate with the temperature gradients and the ice lines you'd expect, shown by these vertical lines on the right. Now, if I can do, yeah, so this is one such system, and inconveniently, they are not actually one-to-one transposed in the two diagrams. This is, I don't know why, these are from the same paper, but they clearly didn't think that far ahead. So you've got your ice lines do not line up with where your ring structures are. So these gray shaded, these shaded regions are your rings, the ice lines are the vertical lines. You see they do not line up. So this begs the question, what therefore is dictating the ring-like structures? And the answer is proposed to be rather that there are, it's the forming protoplanets. So already in these protoplanetary disks, 1 or 2 million years old, if that, you already have enough of a planet or a protoplanet in those systems to start to dictate the structure that you observe in these protoplanetary disks, which is great, but that's problematic also because that means that linking debris disks, protoplanetary disks, and the solid planetesimal architectures of both becomes more complicated because you have to take into account the planets. So flipping over to debris disks, which are much older, sort of beyond 10, 20 million years old, the gas disk from the protoplanetary disk phase is gone. You're looking at an optically thin disk, whereas protoplanetary disks are optically thick. And you're therefore sort of tracing dust grains, planetesimal belts directly. So this is usually at far infrared, a millimeter wavelength, because it's easier to see against the contrast on the star, but asteroid belt analogs do exist. They're just harder to see because of the large contribution of the stellar photosphere and also angular resolution. So you're all basically looking at unresolved point source for most asteroid belts. Not all, but by analyzing multi-wavelength imaging, scattered light, scattered infrared light from Hubble at 8 band, then you've got far infrared, Herschel at 70 microns, and then ALMA millimeter wavelengths. By combining these bits of information, you pull up it with the emission in this SED. So SED plus imaging gives you dust grain properties such as size distribution, minimum size, albedo, something about the shape depending on how much of a scattered light image you have, and also something on the composition in order to fit all these data points. And so this is kind of the analysis, my bread and butter kind of analysis to do this kind of work. And this is kind of typical debris. This is HD 105. It's a sun-like star, 50 million years old, about 50 parsecs away. So if you get enough of these together, which is what the Herschel key programs, dunes and debris were looking into, you can start to pull in a population study of debris disks. So the real power of Herschel was that it was a large space telescope for the time. It's 3 meters, and that gives you, a much better angular resolution than had heretofore been possible. So Spitzer was quite low angular resolution. It was only a 70 centimeter telescope, I think. Herschel, same wavelength, 70 microns, far infrared, much better angular resolution. This means you could start to actually spatially resolve the dust emission from these outer cold planetesimal belts and start to pull in the idea of, okay, what's the structure of these planetary systems? So how big are these debris disks that we're looking at? Whereas previously you usually only had the emission, you didn't have the complementary imaging to actually tell you where the dust that produced this emission actually lay around the star. So here you've got an image where, so the black line dictates this is where you couldn't resolve anything. So any disk below this line. So you have got spatially unresolved disks, but they're all lie below this line here. So these are all the spatially resolved disks that I found in Herschel archive. And you see for spectral type or temperature, the stellar temperature is given by the color bar, and the size of the disk is given by the dot size. So that's, I think, 200 AU, 100 AU in radius, then 50, and then 30, I think. So you see, and typically you see, okay, disks are bigger around A stars, but also A stars are further away, so you're missing a few of them. And yes, you start to about 150 AU stop seeing many debris disks, certainly around sun-like stars down here. So with that kind of size scale, so now you've got from the far infrared, you've got a sense of the scale of these planetary systems from the debris disks, and then also from the millimeter. So this is work by Luca Matra, who did actually before the work I did. So this is the kind of the OG version of that plot. Is here you see radius of the disk versus stellar luminosity, and here you see, with a trend line through the middle of it, the solar system is in red, and protoplanetary disk CO ice lines are in orange for two systems. And the error bars here are the width of the disk. So it's not the error bar in the radius, it's the width of the disk with the disk peak radius as defined from the millimeter imaging here as the dot. And you see here, there's broadly speaking a trend. There's a very big spread in the range of widths you see, but overall there is a trend, and this trend is consistent with the idea that it follows the same kind of trend as you see for the CO ice lines, carbon monoxide ice line. So from the protoplanetary disk, where you've got that carbon monoxide ice line, you could argue that planetesimals might preferentially form there at that ice line, and that then dictates the size scale of at least your cold outer belt for your debris disk system. And you see some of these are very broad, these broad disks. So if you look at the broadest disks, as Seb Marino has done here using the ALMA data, if you look at them with high enough angular resolution, and you get enough beams across the disk, for these few systems here, most disks, I'd say, that actually have been observed in high enough angular resolution show substructure. And that shows the kind of substructure that's either due to perhaps an embedded planet carving out a gap in these broad disks, ejecting material from its orbit, or you see maybe it's a planet interior to the disk, and that's just a resonant gap, so similar to the Kirkwood gaps in the asteroid belt, the solar system. So you see broad belts seem to exhibit structure involved in planets. So disk-planet interaction is very important in the interpretation of these planetary systems. And that means that if you've got material being moved from a broad belt, it has to go somewhere. And that brings us on to talking about how you get a scattered population of planetesimals. This is HR 8799, very famous system. It's got 4 directly imaged planets as shown here in this animation. And you can compare here, this is the size of the debris disk, and the planets are all very close interior to this disk. And you see here this model simulation comparing the solar system with its scattered belt population with the inferred scattered population of planetesimals they required to reproduce the debris disk structure they observed from both the far infrared and the millimeter. And so this disk in particular requires a scattered planetesimal population producing dust grains in order to reproduce. It can't just be a single belt, it also has to have a scattered population with eccentric orbits in order to produce the architecture observed. So if things can go outward, they can also go inwards. And so what you need to do in order to trace these bodies going inwards is a large millimeter interferometer, such as the one shown here. This is ALMA. So ALMA is going to be very good at finding these debris. It has been so far, but it's going to go up a notch in future with the results coming from the Reason survey, which was led by Luca Matra. Covered 72, I think, debris disks with both ALMA and SMA, finding their architectures and tracing the structure of those belts. That paper is in prep. And also on top of that, we now have an ALMA large program looking at debris disks, like a dozen debris disks or so, in very high detail, trying to trace both the radial structure, looking for those planet-carved belts, or what we think of planet-carved belts, and also the vertical structure, looking for evidence of stirring, so a scattered population vertically from inclinations. And so this, in the future is bright for debris disks because we have this ALMA helping us trace these architectures induced by planets. And so to give an example, the best and biggest example of any debris disk is Beta Pictoris, nearby A star, 20 million years old. It's got dust gas, it's got everything going on. It's edge on, so it's very easy to see on the sky. It was the first spatially resolved disk in scattered light in 1984. And you can see here it's got a warp, it's tilted, it's got an asymmetric. So it was also the planet, or there are now 2 planets now, there's B and C around Beta Pictoris, but the planets we expected to see around Beta Pictoris were actually inferred from the disk structure. So this kind of links together the idea that your debris disk, by looking at your debris disk, you can look into the planet population that's perturbing that disk. So as I said, where you get planetesimals, where you get disks, you don't see planets, and then they interact with each other. So this is Beta Pictoris, and that's got these cometary bodies so these collisions here, this gas, this volatile carbon monoxide gas is being produced by collisions between cometary icy bodies in the outer skirts of this planetary system, and that gives you these cometary bodies. And so these cometary bodies have been known for a while. Back in 1994, something like that, Hervé Boost did a paper on falling evaporating bodies. They refused to call them comets because someone protested, but they came up with this idea that these falling evaporating bodies passing very close to the Beta Pictoris. You could see the metal lines. This is hot metals in absorption against the stellar line here, and velocity shifted compared to the static disk. You can see at various velocities as these cometary bodies swing around the star, and you can see they can occult a large amount of the star as well. So you can get deep absorptions, large amount of the star. So you get here, you've got two populations of depleted and volatile rich, or like dusty, should we say, cometary bodies going around these stars. So these are basically comets, analogous to ones in the solar system, where you get these sun grazing comets that go around, and you see them in those SOHO images. This is happening around other stars. And there are now a few systems we know of with cometary, exocomet type behaviors. But Beta Pictoris is still by far the biggest and bestest. And you can also trace these in photometry. So if you have very high sensitivity, high cadence photometer in space, this is from the Transiting Exoplanet TESS, so the Transiting Exoplanet Survey Satellite. You see here this kind of characteristic shark tooth pattern of nothing, then occultation, and then this long tail as solid body tail goes past, and you see it's a long tail hit. It's a very characteristic shape that's not clearly a solid body because it's not a symmetrical transit. And so these have been traced. Now they found some more. This is the first paper that identified these in the time series data. There's been a couple more since then, finding more events. And as I said, sorry, just to repeat myself, here you see solid body transit is symmetrical, but your dust cloud transit here. So if you've got this works just for comets as well as you've got these evaporating planets as well. They have the same kind of you've got a tail of material coming off the planet or comet, and that produces this asymmetric transit shape here. And so the other point that needs to be made is that exocomets are also very good because they stick around. So around white dwarfs, you see contaminated white dwarfs with spectral lines. So that material must be deposited relatively recently because it will be sucked into it won't be buoyant in the white dwarf atmosphere or get sucked down if it's metals. And so you can tell from contaminated white dwarfs, you've got cometary populations like being pulled in or flying in and being ripped apart and pulled up by these white dwarfs. So you see this is the remnants from a main sequence planetesimal belt population. So, and if you look at the material in the atmosphere of the white dwarf or in the gas disk around the white dwarf, if it's pulled up enough cometary material, you can tell what the composition of those planetesimals were. And obviously those planetesimals are what made the planets around the system. So if you want to know what your planets are made of, you need to look at, you should probably look at the planetesimals that are being destroyed in order to infer what those bodies were like. So in that original planetary system. And so here, this white dwarf system here, and here's a few other examples. So you get atmosphere contamination lines in various metals, and astronomically speaking. And so so the comets are very important because they give us a grip on both the planetary system and the probing blocks of those planets. And now we've got stuff like JWST, which can do the planetary atmospheres and things that looking at the composition of those bodies that around those planets that probably went into making up those planets would be a good idea to get a grip on what they're actually made of inside and compare them to the solar system bodies, where we can get a very good look at the planetary system, a very close look at the planets inside our own system, and then compare them to ones outside. So as I said, time series monitoring, very important for catching photometric measurements of these exocomet transits. And so this is where space-based missions, so Kepler originally was designed to find Earth-like, Earth-sized planets in around sun-like stars, one AU orbit, one Earth radius planet. It was very successful. So this is the original field, and these are the K2 fields along the ecliptic plane. And you see, so they lots of high cadence observations, and they can trace, with millimagnitude, micromagnitude precision, the photometry of stars, which is the kind of sensitivity you need in order to detect these small dips from cometary bodies. Likewise, moving on, so currently we have TESS. It's just gone into its fourth year. It's flipped over again anyway. And so you've got, observations of the whole sky. So whereas Kepler was observing, one single field continuously, sort of 3.5 years to observe, to find its planetary companions, TESS is doing something similar, but it's observing the whole sky. And so here you've got, it's full sky coverage using TESS, so covering many more stars, but in a similar way, high cadence, high sensitivity observations in photometry. And so the outcome of this for Kepler was this Tabby star. So this is the Little Dippers. So this is the kind of object I want to talk about today. So this had this aperiodic, these very deep dips. So this is a few percent in light, but no periodicity, and quite deep and very asymmetric dips. So these clearly aren't. It's not a transiting planet. It doesn't seem to be stellar variability. It was very weird. So and this is occurring over several hundreds of days, so in a long period, over a long time period as well. So it's not a single event. So the question was, okay, what's going on with this? And people had various ideas. Alien megastructures got mentioned, and so basically the idea was, we don't know, therefore let's just make stuff up. Of course, the answer wasn't actually aliens. It's never aliens. And the answer actually is, if you do multi-band photometry, sort of tracing some of these dips at multiple wavelengths, you can then see that what you're actually seeing is wavelength dependence of the dip transit. So you can say, okay, it's dust grains of some size. In this case, so here we're looking at time series photometry of Tabby star, KIC, whatever it was, in B-band R and I, using several different observatories, and you can see the colors, depth ratios here for these 4 events, and you can see how it changes. And so by comparing the color ratios to various materials, you'd expect, given sizes of dust grains, you can start to pull out what kind of dust grains are responsible. And so yes, so the idea now is that, and they made some predictions in terms of the periodicity they expected to see for this kind of event around Tabby star, and they sort of think it's now a few years periodicity for this eclipsing material that's this exocomet swarm, as it's now believed to be. What creates the exocomet swarm in the first place is still an open question. And so you could get perturbation of a planetesimal belt by a planet potentially, or you could get, for example, a stellar perturber at a wide orbit could produce through the Kozai-Lidov mechanism. You could get excitation of planetesimals onto eccentric orbits through. You don't need a planet inside doing the perturbation. You can have a stellar companion outside producing the excitation to produce the comments you see here. So yeah, so planets not necessarily required, but I like planets, so I'm going to assume it's planets. So now they've got a whole menagerie of these things. You've got this is from a paper. This is a couple of years back now. This is there were a dozen of them at the time, from various authors going through these time series observations, various variability studies. And they sort of pulled out all these events in these objects at a few percent. This is the fractional extinction is only about 1% or so for some of these, even less in some cases. But you see, it's always got these characteristic asymmetric dips. So it's probably not planets, or it shouldn't be planets if it's asymmetric, unless the planet is evaporating, which is a different question. But yes, in summary, you can say, okay, so the planets where the little dipper stars are interesting because you're starting to pull them out. As soon as you get these time series, long period, high cadence observations, you start seeing them. So they do exist. And there's quite a few of them. And it's quite hard to explain, given our current understanding of how planetary systems look, and the fact we don't see any in the near vicinity. We haven't seen any yet until we did this. It's difficult to explain how they occur, because our biggest, brightest example of a debris disk, Beta Pictoris, with a very edge-on disk, so the material should pass in front of the star from our point of perspective, doesn't exhibit the same kind of little dipper behavior that we see in these stars we see. And these stars are much further away. So they're like 100 parsecs, 200 parsecs away. So they're very far. And they don't have any infrared excess associated with a companion disk, which marks them out as being different from these very young systems, these dipper systems, which have optically thick misaligned or behavior, but those are very much young stars with infrared excess, whereas the little dippers don't have an infrared excess associated with circumstellar dust. But obviously, we see from the presence of the occultation, there must be some dust there and something producing that dust in order to create the occultations we see. So yes, finding out where this material comes from is very much an open question and an ongoing line of inquiry. And so here's kind of the latest, greatest paper. So Eric Schmidt did this, and he's pulled together a kind of HR diagram, and these show you where the planets lie. You see not very many very hot stars. So to clue you in here, debris disks are more commonly seen, should I say, around A stars. About 30% of A stars in the solar neighborhood have a debris disk that we can detect. Sun-like stars have about 20%. So there is some spectral type. It may be selection bias, but you get more disks around A stars is the point here. But you don't see little dippers, you don't see. So you don't see any little dippers around those stars. So, and then also likewise, M dwarfs, you don't see around these very low luminosity, very low temperature stars. You don't see little dippers around those stars either. So there's questions about why we see the population of little dipper stars we do see. And that needs to be looked into as well. So so there's very many open questions about the nature of these objects and why the phenomenon occurs. So this brings me to the talk, the sort of thing I want to talk about today, which is 21QJ, which is identified in the Old Sky Automated Survey Supernovae survey. It finds transients, it flags them up, it releases. There was an astronomer's telegram that went around about this object, and so we followed it up with some time from the LCO telescopes, 1 meter telescopes in SDS bands to follow the photometry of this object as it went into this dipping behavior, as you can see here from the light curve on the right with magnitude here. So you see here, it's normally about 13.7 magnitudes in G prime, and it dropped to 17 and maybe down to 20. So this is between 95 and 99% of the starlight was occulted during events in this from this object, which is, if you compare that to Tabby's star, the original, which had 20% deep occultations of the, it's an F star, but it had 20% deep occultations. This is a G star, sun-like star, that has 90% deep occultations of the star. So it's much more extreme. There's a lot greater density of dusty material around this star producing the observed occultations. It's a much more extreme version of the same, we think, the same object as Tabby's star. So here's the kind of the light curve just from the observations we took from LCO, and you can see we got 4 bands. We thought we saw kind of 2 repeat events here, which were very, very deep. And then we thought, okay, well, maybe it's periodic, and this is about 30 days apart, roughly 30 days apart. So we tried later, and it seems that either we weren't lucky enough to catch it at the deepest point, or the nature of the cloud or whatever's doing the occulting is changing over time. And you see it goes from being quite narrow and deep to being broader and flat, and maybe even turning into 2 separate events here. So there's evolution of the dust cloud as time goes by, as it spreads from whatever initial point. So you can identify occultation events. So you can do this very simply, 18 events in the light curve. And if you put I haven't put it up here, but if you put a size distribution, you see there's more shallower events, which is what you'd expect from size distribution of objects going past. And so the main key point here is, as I showed earlier for Tabby star, is here with the multi-band photometry, which you don't get from Kepler or TESS. All you get from Kepler and TESS is white light or single band measurements telling you the total intensity change. With the LCO observations we've got here, you can see there's color, and so therefore you can color plot, and that gives you a reddening vector, and that tells you the size of, you can model, sorry, I didn't tell you, but you can get the modeling the size of dust grains for a given assumption of material. And so here you see with the 4 bands we had, we can do 2 color plots. And this gives you, you see here that generally speaking, the occultation lies over here. For most of the events in these very 2 deep events that I showed you on the light curve at the start, lie over here. So there's something different between these events compared to the general occultation in color space. And so if you fit those with a dust grain model and some assumptions, you can come up with, most of these seem to be, sub-micron sized dust grains, 0.4, which is interesting, because that's smaller than the blowout radius for the given assumed material. So that means as the cloud and the occultation appears to be becoming less occulting and less material, that's good, because this material could be blown away by the radiation pressure from the star. So that hangs together neatly as a story. And you've got this material over here that's 2 microns in size, maybe, or at least that's the size upward to which we can trace it, because obviously this is only a limited wavelength range of color points, and therefore to trace larger dust grains, you need longer wavelengths. So we haven't got that information. So we're kind of limited in the size of dust grains we can trace, but you get the idea. So if you put that on a spectral energy distribution, so looking at, this is the occultations in G, R, I, and Z. You can see here it goes down quite a ways. And you can see over here in the infrared, this is archival photometry. And you can see there's no evidence of infrared excess in the archival photometry. This sort of tells you that it's probably not a dipper star. because there's no evidence of a protoplanetary disk around the star at near-infrared wavelengths. This is like this is WISE and glimpse photometry from glimpse being one of the Spitzer surveys, and you've got WISE out here, which is more of an upper limit, but I plotted it up there like that, and you've got the two mass here. And so see here, archivally, in past times there was no evidence of infrared excess, but if you look at the light curve through NEO-WISE, this is in WISE 1 and WISE 2, so 3.4 and 4.6 microns in blue and green respectively. You see that at some point something happened and the WISE photometry changes. I checked the other stars in the field and other stars which have the same little dipper phenomenon. None of the other stars like that show this similar behavior. So we think it's relevant to the star. It's not an instrumental problem with NEO-WISE or something to do with the field. So it seems to be very characteristic of this object alone. But you see the WISE gets brighter, so the infrared excess increases, or infrared, so you get an infrared excess, should I say, for the star, but there's no dipping. So there's excess dust around here, but there's no dipping occurring. And then eventually you get over here, 2-3 years later, and you start getting dipping. So something happens to put this material into the line of sight. And you start seeing here, you've got the trail off from the assassin observations here as it dips off and starts going there. There's an occultation occurring, and then this is where we are right now, down here in the yellow dots. And so so you've got an event that occurs over here about 3 years ago that produces a dust cloud, and then eventually somehow that dust cloud comes into the line of sight according to our viewpoint. So this brings us to you have to start thinking about what's causing this dipping phenomenon. And so obviously you need something to produce circumstellar dust. And then you need to get that dust into the line of sight, and it needs to be optically thick. So it's different from debris disks. It's not like you can't just have a debris disk doing this. It's something more than that. And so there's a few ideas that people have put forward in order to explain this little dipper phenomenon. And these are all, they're all equally probable, I guess, depending on the statistics you think in terms of the population of the bodies that would be causing the occultation. So for example, a single very large exocomet, the size of Ceres disintegrating or something, compared to, a bunch of smaller Hale-Bopp type comets, where you expect more smaller things. So maybe the smaller swarm is more plausible than a single large thing being thrown in. And so in terms of what we've done for Assassin 21QJ, the two most plausible mechanisms here are these two, either a catastrophic collision in the interior of the system, so something collides and then it comes back round and you sort of see the interaction of the debris stream, or you see something's happened and you get some comets are produced and then they've been processed, their orbits have been processed, so they start to transit the line of sight somehow. Yes, so the mechanism to get them into the line of sight for 21QJ is unknown, but the scenario is kind of sort of defined in terms of what must have happened, but we don't know why it happened or how it happened. And so this is, a schematic diagram here to hammer home the point. You start off with something small, maybe not transiting, or maybe it's transiting, but just too small to be detected in the dips. And then something, at point 2 here, the WISE, you get an infrared excess. So the surface area increases. It's warm. This is sort of several hundred kelvins worth of dusty material. It's within the orbit of Mercury, because this is only a sun-like star, so it's not very luminous. So it's, several hundred Kelvin dust inside, 0.2, 0.3 AU. And then somehow, but it's not transiting for a few orbits. And this is, if there's 30-day periodicity here, that's an orbit, and that's 0.2 AU. Somehow it's not occulting the star for a few years, and then something happens to put it onto the line of sight between the star and us. And so that's as far as we've got with 21QJ, and I will leave you with the summary and conclusions. And yes, I'll take any questions you have.
Yeah, thanks for the talk. Would the same model also apply to Voyager star? Would that also explain the behavior in that case?
Good question, because it might not just be one thing and one thing alone that's producing all these little dippers. So I think, it should be, I think it should be fine that whatever happened here is the phenomenon is similar enough that, yes, you're producing similar behavior to Voyager star, so it could be the same mechanism. But yeah, with dynamics, any dynamical interaction is probably unique. So yeah, it could be, some kind of dynamics that's kind of like magnetic fields. It's a very broad topic, and it's the unknown box. So yes, it could be interaction dynamically somehow, but is it exactly the same thing? So is it, an asteroid belt or something being perturbed, or is it a star that's doing planetesimal belt perturbation? Don't know. And that's why finding out what the architectures of these debris disks is important, because around these little dipper stars, because do they have outer belts that are there exist to produce these bodies, or does it have to come from some other system inside? And so you can start to rule things out the more you know about the system around these stars.
Any other questions?
Yeah, but the WISE, it says what you did. How good is this? Is it well confirmed? I mean, it's
Great question. So yeah, so if you look at the WISE photometry, obviously the error bars are on there, but you don't see the calibration uncertainty, and that's 0.05 magnitude. So there you go. If you've got a magnitude change of less than about 0.15 to 0.25, it's not really plausible. There's so many stars in WISE that you see some weird things, 1 in a million. So in this case, yes. So for the WISE 1 band, so the shorter wavelength, 3.4 microns, the change in brightness is significant enough that it should be legitimate. For the WISE 2 band at 4.6, it's a 2.6, 2.7 sigma change. So it's not, you can't say that with any confidence. So it's tentative, but the point is that none of the other little dipper stars are doing this or have done this in the past that we can see in WISE photometry, and none of the other stars in the field in which 21QJ resides on the WISE images does this either. So it's something unique to this star, I think. It may not be formally significant, but I think it's circumstantially, it's enough to look into it and try and pin something on with it.
have you observed that? This is 3 microns.
Yeah, the problem with this is from the SED, as you can see, this is 10 millijanskis. So if you're looking for an excess of, it'd be about 10 millijanskis in brightness with the WISE 3 and 4. Sorry, WISE 1 and 2 out here. You can't really do that from the ground. You need space-based photometry to do that. So if anyone who's JWST time, I wouldn't mind having some to look at it. Yeah, don't tell them the plan. Don't tell them the plan. But yes, yes, infrap. The deadline isn't for a while yet. So so the idea is hopefully to follow this up with some kind of space-based photometry, because you need the sensitivity that you can't get from the ground. Is the problem.
Any other questions? Yeah.
Can you make a prediction of what's going to happen now? I mean, the deeps seem to be getting shallower, and it's going to go quiet for some time and then come back after some years. So what would be the expected?
Yeah, so I would expect it. So as you see from the light curve, okay, where's the good light curve? Yeah, here. So you see from the light curve, here will do. You see, yes, it is getting shallower, and over time, you expect it to fall. This isn't the end of it. There is actually a bunch more photometry on top of this we got from a monitoring program, but it's showing the same kind of, I want to call it exponential, but gradual trend towards zero occultation. And yes, if it's going to come around again, it probably won't come around again with the same strength, obviously, in terms of the dipping. But yeah, that's why looking at the infrared from the emission part becomes important, because you don't need to see a dip to see the dust emission is the thing. But yeah, no, I would expect it to basically dissipate to nothing unless something else happens to produce another collision for some reason. But yeah, and because you can see that from the WISE photometry as well. I mean, yes, okay, it's tentative, but you can see it's gone up and then it's going back down towards nothing again, basically. Back there.
Do you expect to have any features showing in high resolution spectroscopy?
High resolution spectroscopy, I would hope there would be some features. Unfortunately, we never got spectroscopy when we put in the time to monitor this. That was an oversight on my part. But yes, I would expect there to be some narrow spectral features in the optical spectrum or the UV spectrum, probably. In the infrared, I'm kind of hoping from the inferred grain size that you could see a silicate feature at 10 microns or so. That would be, again, that's the motivation for JWST, is like see if there's a silicate feature and therefore see, is this crystalline, is it amorphous, ... the usual things.
Yeah, we got high resolution spectroscopy of Tabby.
Oh yeah.
During the median months after the discovery, and there was a big consortium of also people getting data. It was very
Okay.
I think there were some dips after the main event that happened. We had a tinker system even.
Oh, great.
And I would not tell you this if somebody was looking at it, but I suspect that nobody is looking at it anymore. So maybe it worth to check at least to see if there is something on the image to one of the dips. If there is expectation that you can compare to where there was nothing happening because it happens. So it's optical up to 1.5 microns. So from some lines, potassium.
Yeah, there should be some metal. I'd expect to see some metal lines in there if it's hot enough. So
Well, it's checking.
yeah, I just don't have a look.
There's a line that shows that that's not expected for some reason, but I'm not sure it was checked properly at the time. So
Yeah, okay. Yeah, and if you can link that back to the photometry as well, then you can see where it's deepest dip. So hopefully you get a spectrum about that time. Yeah, and yeah.
there were triggers. So I remember that there were triggers. So we only took spectral when something happened.
Okay. Oh, yeah, that's worth looking into. Then I'll see if I can dig that out.
Okay, any other questions? Not? John, see you again for a nice presentation.
Thank you.
Now there should be pizza in the patio. Let me mention two things that I forgot at the beginning. Last year we already had this idea of doing debates. In the end, we didn't implement it because there were not too many suggestions. This year we are going to do it, and we are already organizing one probably in November. Right, so the idea is that two people come here and there's a topic, and each of them do make a presentation of one point of view, and then there is a discussion with the audience. The other thing that we were planning to do that we didn't do last year was the idea of having, a special topics. Idea is that people propose, especially I think this is useful for students. Like general topics doesn't need to be like the cutting edge thing, right? General things. And then if there is enough, let's say people proposing them, then we can try to arrange for having someone to give one of the seminars about it. So I will send an email again. I mean, just mentioning this thing of the doing and these two things. So please try to participate. Okay, now enjoy the pizza. Thank you.